Okay, I just wanted to sort of quickly go over some of the things that we did last time. So one of the things we did is we defined this homomorphic product of two graphs, right? So the vertex set is just the product of the two vertex sets, and then this adjacency condition sort of encodes somehow some conditions from this homomorphism game. So these two ordered pairs are adjacent if G is equal to G prime and H is not equal to G prime, or if G is adjacent to G prime and H is not adjacent to H prime. In particular, this means that if I fix a first coordinate here, right, and I vary the other the H coordinate, then I get a clique in this graph, right? So I can partition this graph into cliques, the number of cliques equal to the number of vertices in G. Okay, we also defined a projective packing of a graph. So this is just an assignment of projections to my vertices, some D by D projections. And I want adjacent vertices to get orthogonal projections. And we say the value of projective packing is just the sum of the ranks of all these projections, but we normalize by dividing by D. And then this projective packing number, this alpha P of G, is just the supremum of all the values of projective packings. And we need supremum because we don't know that we can replace it with max, right? Maybe it's not attained. We don't know that we can't replace it with max. There's no known example, but we suspect that you can't replace it with max. We also showed last time that having a quantum homomorphism from G to H is the same as having this certain set of projections that satisfy this summing to identity condition. So if you fix G in sum of H, you get identity, and then you get this orthogonality in certain cases. And so this case, remember, is sort of implicit actually from the first condition, since we're dealing with projections. If you sum to identity, then if you have a bunch of projections that sum to identity, you have to be mutually orthogonal, right? But then this other condition is not implied. So if you have adjacent G coordinates but non-adjacent H coordinates, you should be orthogonal. And we showed that it's also equivalent to having a quantum homomorphism from G to H to have that the projective packing number of this homomorphic product is equal to the number of vertices in G. But that's not quite right. We actually need it that this value is attained by some projective packing. And I'm going to be lazy and I'll just write equals with a little dot over it to mean that it's equal and it also attains this value. I don't want to have to write out has a projective packing of value blah every time. Okay, and maybe something I should have mentioned explicitly, but hopefully it was implicit, is that if I have a homomorphism from G to H, this implies that I have a quantum homomorphism from G to H. Okay, so maybe in terms of the game, you can imagine that, well, if I can win the game classically, I should be able to win the game quantumly. In terms of these projections, well, I just take whatever my homomorphism from G to H is, right? So this is subhomomorphism F, and then I make E sub G, F of G identity, and everything else is zero. The other thing is that there's also a classical analog of this result, where that says that you have a homomorphism from G to H if and only if the independence number of this graph is equal to the number of vertices in G, right? And this is straightforward. I mean, as I said, this graph is sort of partitioned into these cliques, right? One for each vertex of G, right? So if I can get at most one vertex from each of those cliques, and if I can actually get one vertex from each of them, then essentially I've chosen a vertex of H for every vertex of G, and that gives me the homomorphism. Okay, right. So let's recall I can define clique number and chromatic number in terms of homomorphisms. So the clique number is just the maximum K such that a complete graph of size K has a homomorphism to G, and the chromatic number is the minimum K such that G has a homomorphism to K sub K. I have a notion of quantum homomorphism, so I can just use that to define a quantum analog of chromatic and clique numbers. So I just add QT everywhere I want to add it, and now I have a notion of quantum clique number and quantum chromatic number. Okay, and actually somehow, I guess for whatever reason, in practice we often care, instead of about quantum clique number, we often care about quantum independence number, to denote by alpha QT. And this, of course, this is just omega QT of the complement. of the graph G. Okay, so what we're going to look at today mostly is this quantum independence number. And one of the interesting things with the quantum homomorphisms is that is to sort of see when there are quantum analogs of sort of classical results, which is maybe often what you would expect. So for instance, we will get an analog of this with quantum independence number today. But then sometimes it surprises you when you have some sort of kind of strange behavior of these quantum homomorphisms, and you end up with some classical result that doesn't have a quantum analog, and in fact has a counterexample. And we'll see examples of both. And since we're going to be focusing on this, I just want to explicitly write out sort of what it means to have a sort of a quantum independent set of size k in terms of these projections. So I will say that so this quantum independence number of G, it's at least some k, if and only if there exist projections E sub I G for I in the set 1 up to k and G and V of G, such that if I sum over G identity and this E I G E J G prime is 0 if I equals J and G not equal to G prime, I not equal to J, and G is either adjacent or equal to G prime. So I'll use this to mean adjacent or equal. Okay. And this is just directly, well, I've covered it up now, but this is just precisely these two conditions, but we have to be a little careful because we've taken a complement here with its independence number. That's why I wanted to just write them down explicitly. Okay, so this is quantum independence number. I mean, we also have already defined this alpha p, which is, I mentioned last time, is kind of like an independence number as well. Right? If I have an independent set in my graph, I can assign identity to all of those vertices and a 0 everywhere else, and that gives me a projective packing of value equal to the size of the independent set. And this is also kind of quantum-y, right? In the terms that it's, you know, defined in terms of these assigning projections. This is a little bit more complicated looking, right? Because now I have a projection for every I and every G. But presumably there should be some relation, hopefully, between these two things. And actually there is. In fact, the quantum independence number is less than or equal to the projective packing number. And I can be a little bit more precise. I could say that there's always a projective packing of G with value equal to the quantum independence number of G. And okay, the proof is not hard. So if I take E sub I G, I and K, G and V of G, such that, you know, give a quantum independent set, being a little sloppy in my terminology. I mean, I haven't technically defined what is a quantum independent set, right? I want to define what it means to have alpha QT being bigger than something. I also never defined what a quantum homomorphism is, right? I only define what it means to have a quantum homomorphism from one thing to another. But that doesn't matter. Okay. So if I have these projections that give me this quantum independent set of size k, right? What I do to get a projective packing is well, there's not really a whole lot you can choose to do, and then you do maybe the most obvious thing. I define my projective packing as follows. Just I sum up all of these, okay? And I need to check that this is a projective packing, but this is fairly straightforward. First of all, I need to check that these are projections. But you can see from here that if I'm fixing G here, right? So I have G equal G prime, right? Among these things in the sum, right? And of course, for distinct i's, I get orthogonality. So I'm summing up mutually orthogonal projections, and that gives me a projection. And then checking the orthogonality for adjacent vertices, again, is something that's straightforward. And then what's the value of this projective packing, right? Well, let's look at, we want to take the sum of the ranks. And maybe the easiest way to do this is to note that okay, we want to take 1 over d times the sum of the ranks of PG. For a projection, the rank is the same as the trace, right? And trace is linear, so it's a little bit easier to work with, right? So this is equal to 1 over d sum. Well, I can bring the trace out, right? Trace of the sum over g, but then for each g, I also have a sum, right? So this is the sum over I and g of E, I, G, right? And now if I sum over g first, right? For every I get identity, right? And so then I sum over I just get k times identity. The trace of that is k times d. I'm dividing by d, so this is equal to k. Okay, so I get a projective packing of value k, which is the value of the quantum independent set. All right, so we get this kind of nice connection, and maybe I should mention that, I mean, you can get a strict separation. We'll see an example, but I think the only separations we know, alpha qt is always, we don't know that alpha qt can be strictly smaller than the floor of this alpha p. So that's sort of an open question of whether maybe they're not just related by this inequality, but actually very, very closely related. And maybe there's some evidence that should be the case. Was there a question? No. Okay, so before moving on, I just want to define the sum of a projective.
Quick question.
Yes.
If you're using the other type of quantum homomorphism we talked yesterday, is to get this inequality?
This, like the quantum commuting.
Yes.
So you need a kind of a.
Right? Yes, sorry. Should I repeat the question? Okay, repeating the question. If you use the quantum homomorphism that you defined yesterday, the other one, the quantum commuting, do you still get this inequality?
You need a sort of a quantum commuting analog of this thing.
Using the homomorphic product.
Not using, well, I mean, you will also have an analog of this result.
Yes.
But to define, I mean, the difference is that now you don't restrict to finite dimensional projections. They can be some projections in some seesaw algebra with the tracial state. And then you use this tracial, the value then is based on this tracial state.
Right.
Okay. Yeah, so.
Do you still get
but yeah, then you would get it.
Okay,
You will get it. By the same reason.
Okay.
I don't know if it's written down anywhere, but I'm certain that it's fine. All right. So I will define the sum of a projective packing. So if I have a projective packing that maps G to a piece of G, this is just the sum of all these projections. Okay, so okay, so this is just by definition what I mean by the sum of a projective packing. And the reason I want to define that is because now I can prove a lemma, which, well, okay, we've actually already proved that this alpha qt is less than or equal to alpha p, but we'll now prove it in a different way. And the proof will sort of be slightly more general, so we'll get a little bit extra stuff. Right, so I need to do this one first. So if we have two graphs, G and H, and there's a quantum homomorphism from G to H, and the complement of G has a projective packing with some P, then H bar has a projective packing with some P tensor identity with some size identity. You don't get to specify it, but for some identity, some size identity. Okay, so how's the proof work? Okay, so suppose this is our projective packing of G bar, and then we have the projections that give quantum homomorphism from G to H. We want to define now a projective packing of H bar. So we would define, let's say, Q of H is going to be equal to the sum over G of P sub G tensor E G H. All right, great. So again, I mean, we have to check that it's a projective packing, but it's actually it's of H bar, right? I mean, we need to check that this is a projection, But that just follows from conditions on the PGs and the EGHs. I mean, if I look at two different terms here, right, a G and a G prime term, right? If G and G prime were non-adjacent in G, that means they're adjacent in G bar, right? Then I get orthogonality from this term. Okay. If G and G prime were adjacent in G, right? Then I get orthogonality here because I have EG H and EG prime H. So the H's are equal, but the G's are adjacent. Right. So every term here is either orthogonal from this part or this part. So this really is a projection. And then again, sort of like checking that. Well, I guess we can even. How am I doing on time? There's no clock in the room. 10:50. Okay, well, maybe I'll leave that as an exercise. Again, it's a straightforward exercise to check that if you have two now non-adjacent things in H, remember, because we're looking, we want to find a projective packing of H bar, then they're really orthogonal. And then what's the sum of this projective packing, right? Well, I sum over all H, right? So I can bring that sum inside here. I get identity here, right? And then when I sum over G, I get the sum of the original one. Right? Okay. But of course, one thing that means is that if I have a quantum homomorphism from G to H, then this projective packing number for G bar, okay, is less than or equal to the projective packing number of H bar. All right, because I mean the value, right? If I have this for G bar, I have this projective packing with some P. Right, and what's the value, right? What's the value of this projective packing, right? Well, it actually, we don't know what the D is, or whatever the D is. It's 1 over D times the trace of P, okay? Actually, we can think of this is like the average of the eigenvalues of this sum P. And then when I take the same thing here, okay, this will be some like D prime or something, right? Then now the value will become 1 over D times D prime trace of this, which is of course just D prime trace of P. Right, so the values are the same. Right. Okay, so what this is saying, and if I want to, since I'm taking a complement here, right? If I think of this as kind of like an independence number, I want to think the value on the complement is like a clique number. So maybe I want to write this as omega P, right? Of G is less than or equal to omega P of H. Okay, and so what this is saying is that this omega P is quantum homomorphism monotone, right? So we talked a little bit about that yesterday for homomorphism monotone thing. Okay, now this, maybe I should have mentioned this earlier, right? These are kind of obviously quantum homomorphism monotone because of the way they're defined, for the same reason that clique and chromatic number were homomorphism monotone, right? But there's nothing really obvious reason why this thing should be quantum homomorphism monotone. So this is kind of an interesting result, right? And it shows you that, I mean, this really is some kind of like quantum thing, right? I mean, it's not just, oh, it's projection, so it's kind of quantum, right? It's sort of more, there's more reason to think it's kind of quantum, right? Right. Okay, but that's not actually all this limit gives us, because as I mentioned, right, the value of this value of a projective packing is like the average of the eigenvalues of the sum of the projective packing. Okay. Okay, but I mean, well, if we think that the average of the eigenvalues of the sum of a projective packing is some interesting parameter for a graph, why don't we look at, say, the maximum eigenvalue of the sum of a projective packing, right? But actually, this is already a known parameter. This is equal to log theta. Well, it's the max. Now it actually is a max of the maximum eigenvalue of the sum of a projective packing of your graph. Right. And of course, this means that, well, immediately, right, we get that alpha P of G is less than or equal to theta of G. Of course, the maximum eigenvalue is at least as big as the average of the eigenvalues. It's immediate. Okay, I think this is maybe not the most standard definition of Lobos theta, but this is a valid definition. Right? Okay, but again, though, we get more than that, right? Because, right, from this lemma, right, I can take some solution for theta of g, right, or rather theta of g bar, I should say, right, and then I get a solution for theta of h bar. Okay, and I'm just replacing this sum with this sum tensor identity. Well, that doesn't change the maximum eigenvalue, right? So this means that if I have a quantum homomorphism from G to H, and I use this theta bar, this just denotes theta of G bar, but I sometimes like to make this into its own parameter. This is how it should have been defined, by the way. It should have been defined like this, but it's not Lobos's fault because Shannon defined the wrong graph. He should have defined the distinguishability graph instead of the confusability graph. And he knew that it was wrong because he knew that if you have a homomorphism from the complement of a confusability graph to the complement of another confusability graph, then the capacity of one is less than the other. So he knew that he defined it wrong. So no sympathy for him. Okay. Okay. So it tells us that this Lobos theta bar is quantum homomorphism monotone. And as a corollary of this, what do we get? We get that, okay, well, let's consider the quantum chromatic number. So let's suppose that, okay, well, maybe I will just write down the statement and then we'll see. As a corollary, we get that the quantum independence number is less than or equal to theta bar, which is less than or equal to the quantum chromatic number. Okay, so this is like a quantum version of this like sandwich theorem. This is paper by Knuth. It's called the sandwich theorem, which is sort of about this. Well, the whole paper is really about Lobos theta. Okay, so this gives us an upper bound on quantum peak number and a lower bound on quantum chromatic number. And the way this works is that, well, let's just do the quantum chromatic number one, right? So let's say that K is equal to the quantum chromatic number of G. So then what do we get? We get that G has a quantum homomorphism to K sub K, which implies that theta bar of G is less than or equal to theta bar of K sub K, which is known to be equal to K. Right? So we get that theta bar is less than or equal to K, which was the quantum chromatic number of G. And then the proof for this one is the same. Okay. And of course, I can put this omega p in the middle here if I want, but that's fine. All right. What's the nice thing about this? I guess the nice thing is that, I mean, this is sort of efficiently computable. Maybe that's a little bit of a lie. It's efficiently approximable. Right? I'm always a little unclear about if I actually want to compute it exactly. What does it even, well, I mean, what does it even mean? It doesn't have to be irrational, right? So, or algebraic, maybe, I don't know. But yeah, so anyways, at least you can approximate it, right? You can find the ceiling, right? You can compute the ceiling or the floor. But this is undecidable. This is undecidable. And it's, I mean, basically, I think it was the first kind of non-trivial bound known for this quantum chromatic number. Now I'm out of boards. Maybe I'll also mention that another bound on this projective packing number is the inertia bound. So I don't know how many people are familiar with inertia bound from algebraic graph theory. Okay, but this is if you look at the adjacency matrix of your graph, and then you consider, I always forget how it goes. I'm sure someone in the audience can tell me. You want to look at the number of non-negative eigenvalues.
Minimum of non-positive, non-negative.
Sure, minimum of either non-negative or non-positive, right? But you can weight it, so you can, doesn't matter. Okay. And then that gives you an upper bound on the independence number. This is known for some time, but you don't need to use the adjacency matrix of your graph. You can use a weighted adjacency matrix. So you just need zeros in the right places. And then for some time, it was actually an open question. So if you optimize over all the weightings, right, can you actually get the independence number? then not that long ago, John Sinkovich, I don't know how to pronounce his name, I guess maybe that's right. He proved that you can't always get the independence number if you're optimizing over real weightings. But I guess just a little bit after that, two people, Elphick and Okchun, okay, they showed that this inertia bound, even in the complex weighted case, is an upper bound on this projective packing number. Right? So that means that it can't be tight for the independence number always, even in the complex weighted case, right? Because you can get a separation between alpha and alpha p. Right. All right. So it's kind of nice because you proved something in algebraic graph theory when we were doing some sort of quantum stuff. Okay, right. So we have that this alpha qt of g is less than or equal to alpha p of g, which is less than or equal to well, it's less than or equal to already like Lorentz theta, but in particular, it's less than or equal to the chromatic number of the complement of G. Okay. Just because, well, this is lower bounded by Lorentz theta. But something interesting happens when you have equality here. Well, when you have equality and it's actually attained. So what you get is that you somehow get that these parameters kind of collapse, like somehow if this inequality kind of collapses to equality, then actually the whole thing collapses to equality. So if this alpha p of g is equal to chi of g bar and it's attained, then in fact alpha qt g is equal to chi of g bar. And of course, if this is somehow just the floor of this is immediate, right? I mean, so.
Is the inertia bound in this sequence? It's less than
I would assume it's less than or equal to this, but I don't actually know. So not, Gabriel's saying it's not.
No, he's saying microphone.
What? No, I would assume that it's less than the chromatic number of the complement, but I don't know.
I don't think it sits between these two guys.
Okay, you don't think it's less than the chromatic number of the complement? Yeah, but I just assume it's like the worst bound on the independence number you can get, right? So just assume this, all the other ones are at least as good. Okay, I don't know.
There is an inertia bound for the chromatic number with the 1 plus the ratio of the...
Yeah. I've seen that. Yeah. Okay, yeah. So maybe it has no relation to this at all. It's certainly an upper bound on this. That's what I said before. Okay, so how does this work? Good. Let me check the time. 5. No, okay, I have time. So this is kind of cute, I think, and I think I don't know. It's something interesting about the fact that why should these two things being equal somehow make this other one equal? I don't know. This to me is a little mysterious. Okay, so suppose we have our graph, okay, and suppose this holds. So let's consider an optimal coloring of the complement. That means I have a partition of the graph into some cliques, right? So some clique C1, C2, and so on. Okay, now in any projective packing, all the things assigned to the vertices here have to be mutually orthogonal, right? So if I have some projective packing and I sum up over the G and C sub I, this is going to be some projection, and it's going to be sort of at most identity, right? And this, I guess, positive semi-definite order, right? So in particular, if I take the rank, right, this is going to be less than or equal to D, where D is the dimension of the projections I'm using, okay? And I have that for every clique, right? Remember, and the number of cliques is just this chi of G bar, right? But I assumed I actually have equality here, and that it's attained. And that must mean that I actually have equality here for all I. It's strict inequality here for any of the i's, and no way I can get equality here. So that means I have equality here for all I, but that means that these sum up to identity over any of these cliques. So that means that I get, gives me identity. Okay. And so now I have some subsets of these projections. I mean, somehow going from projective packing to quantum independence number is a little tricky, right? Because for this, I need like these, I need a projection for every, index and every vertex. And also I need that some of them sum to identity, right? And there's no such condition here. But now I've sort of gotten this condition because of this constraint, right? So what I do is I just define this EIG to be equal to, it's going to be P sub G, G, if G is a vertex in the ith clique. Okay, well, obviously these are projections, right? Let's check that this works, right? So these are obviously projections, right? I mean, this is a projection, this is a projection. Okay. I need to check the summing to identity condition, but that's obvious, right? If I fix I and I sum over all G, right? Then I end up just summing these over one of my cliques, which is exactly identity, right? So the summing to identity condition I have just fine. Then I need to check the orthogonality conditions, right? But one of them I get for free, right? The I equal to J, G not equal to G prime, I get for free already from the summing to identity condition. So actually all I need to check is that if I is not equal to J and G is adjacent or equal to G prime, then I need to get orthogonality, right? So if in this case, right, if I take EIG times EJ G prime, well, if G and G prime were equal, right, then they're in the same clique because they're the same vertex, right? Right. So if G and G prime are equal, then actually at least one of these has to be 0, right? Because I and J are not equal. So in that case, I get 0. On the other hand, if G and G prime were adjacent, right, then in the worst case, both of these are not 0, but then the projections from a projective packing and G prime are adjacent, so they're orthogonal. So this is 0, which is what we wanted, right? So this really does give me a quantum independent set of value, the chromatic number of the complement. Okay, so actually this is something that we get now as a corollary, which is something I mentioned earlier, right? So we get this quantum analog of this, I guess I've erased it by now, right? We get that G has a quantum homomorphism to H if and only if the independence number of this homomorphic product is equal to the number of vertices in G, okay? And the reason is that, well, if I look at alpha QT of this product, well, we know that this is upper bounded by alpha P of the product, less than or equal to chi of the complement, which is less than or equal to the number of vertices in G, right? Because remember, this graph, I can partition into cliques, one for each vertex of G, right? And that gives me a coloring of the complement, right? So I can always color it within most D of G colors, right? So I have this string of inequalities. Well, if this is equal to this, right? So if I have this condition, right? Then in fact, I also have that the alpha P is equal to this. And in fact, I also have that the attainment, right? Because we said that you always have a projective packing of value this, right? And so by the previous theorem, I get that there's a quantum homomorphism from G to H. On the other hand, right, if there's a quantum homomorphism from G to H, I get that this is equal to, I get that alpha P is equal to this, and this is attained, which means that it's equal to, must be equal also to this, and it's attained, right? Which by this lemma implies that alpha QT is equal to this, which must be this, right? So we get that for free from here. Okay, so actually you can generalize this a little bit. The proof of the generalization is it's not so much different. I mean, the essential idea is the same. Okay, but instead of using chromatic number, you use fractional chromatic number. So if we have that this projective packing number of G is equal with attainment to fractional chromatic number of the complement. Okay, perhaps I should take a second and ask, does everyone know what fractional chromatic number is? Does anyone not know what fractional chromatic number is? Okay, at least one person. So that means I'll tell you. So, well, there's many different definitions. So you can write an integer program for chromatic number and take the linear relaxation. Okay, but maybe another way, a way that I like, which is more relevant to this, is that it would be the minimum of, let's say, A over B, such that there exists A independent sets that cover each vertex B times. Okay, so for chromatic number, for coloring, right, you want an independent set that hits a collection of, say, K independent sets that hits every vertex exactly once, right? Here, I'm allowing you to now hit vertices multiple times, but I'm sort of like normalizing by taking the number of independent sets and I'm dividing it by the number of times that you hit every vertex. Okay, so that's one way of defining this fractional chromatic number. Of course, we're looking at the complement, so instead of independent sets, we'd be taking cliques. Okay, so what do we get here? We get that there exists a B, implies, I guess, such that alpha P of B copies of G. So when I say B times G, I mean just take B, the disjoint union of G with itself B times. This is going to be, sorry, this should be of QT, is equal to this chi F of B G whole thing bar, which is equal to B chi F of G bar. And this B is connected to this B over here. Okay, I won't go through the proof of this, but I mean, again, the idea, I mean, like somehow we will have these cliques that are covering the vertices of the graph maybe multiple times, right? And you'll get that on each of those cliques. My projective packing sums up to, at most, identity, right? But actually, I will have to have equality for the same arguments before. And then you have to be a little bit more clever with the constructing the quantum independent set, but you can do it. Okay, and so, right. Okay, I'm doing good, actually. Perfect. So that's sort of, actually, this is the construction that we can use to get a nice example. In practice, I mean, we don't really have a lot of good examples where we're using like some higher rank projections in these projective packings. So in practice, right, what happens, it seems, is that you consider some nice set, say S, of n vectors in, say, d-dimensional space, CD or RD or whatever, okay? And then you look at the orthogonality graph. Okay, so orthogonality graph, it just means I should say non-zero or unit vectors, right? So I make two of these vectors adjacent if they're orthogonal, right? So I take the vectors as the vertices, and then two of them are adjacent if they're orthogonal. And then what I want to end up happening is that I want this n over d to be equal to the fractional chromatic number of the complement. Okay, so actually this n over d, so these vectors, right, if I just assign the projection onto this vector to every vertex, right, that gives me a projective packing. What's the value of the projective packing? I sum of all the ranks are 1, so when I sum them up, I get n, and I have to divide by the dimension d. So the value of that sort of kind of natural projective packing is n over d, and I hope that this is equal to this fractional chromatic number. And then I can take sort of some multiple copies of this g, and I get this quantum independence number is equal to this. But what I need also is that, so I also want this alpha of g is less than chi f of g bar. Okay, so that's another condition I need. And then I will end up with, I'll end up with a graph where when I take multiple copies, I get quantum independence number is strictly bigger than the independence number. Because taking multiple copies it just multiplies the independence number. All right, and such a set of vectors, well, it's not exactly this, but it seems that a good place to look are at Koch and Specker sets. This is a notion from quantum information. I'm not going to go into the detailed definition, but you can Google it and you'll find it. Okay, and I'm not saying that this is exactly the same thing, but somehow pretty closely related. All right, and now I will put this. I have just like one slide I want to put up. So I should mix this.
I'll have to come down.
Oh, you have to go down. Ah, okay.
I think you have to remove the white piece of paper. Oh, it's okay.
So Dave,
Yes.
I was gonna ask something while everything was being turned on.
That's fine. Actually, I should have, before I get to this, I should mention, what do we have it? Alpha QT, maybe it's behind this one. I think it's behind this one. Where's it at? Oh, yeah, here, right? Okay, so actually, I should have pointed out, right? This tells me that I can always get a separation, right? So if I have G, which does not have a homomorphism to H, but it does have a quantum homomorphism to H, then that implies that this alpha of this product, the classical independence number, is strictly less than the quantum independence number, right? Because, well, I have this, so that means that this is equal to the number of vertices in G, but I don't have this, so that means that this is strictly less than the number of vertices in G. Okay, so whenever I have any example of a pair of graphs where there is a quantum homomorphism but no homomorphism, I actually get a separation between independence number and quantum independence number. So in some sense, everything can be reduced to independence number. And that's actually true even more generally for these types of games that like the homomorphism game. They're called non-local games where you are sending these players some questions and they have to respond with some answers according to some rules. As long as you have this consistency condition. So if whenever you send them the same thing, they have to respond to the same thing, right? Then you can always somehow reduce this to a question, like whether or not there's a quantum strategy, you can reduce it to the question of what's the quantum independence number of some graph. Okay, so we can construct lots of examples like this. For instance, tomorrow we'll look at examples with a separation between chromatic number and quantum chromatic number, but any of those will also give you a separation here. Now, so here's a Koch and Specker set. Is there a way to point or right? Okay, so it says another Koch and Specker set, but this is because this is slides from some other course. Okay, so this is a Koch and Specker set. So you have actually you have 18 vectors here, and you have 9 orthonormal bases. That's the columns, 9 orthonormal bases. It's in R4. And the colors correspond to, like, see, these are the same vector, right? So the colors somehow correspond to what the vector is. Every vector appears in exactly 2 of these orthonormal bases, okay? So I can actually think of these bases and the vectors as a graph. So I have 9 bases, so I get a graph with 9 vertices, those are my bases, and then 2 of the bases are adjacent if they share a vector, right? And this graph is actually just the Paley graph on 9 vertices. It's also the Cartesian product of K3 with itself, which is also the categorical product of K3 with itself, which is also the line graph of KC3. Okay, and now because of the way this graph is defined, these, if I take the line graph of this, then I just get the orthogonality graph of these vectors. Okay, actually that's a bit of a lie. There's some extra orthogonalities, but I will get a graph where this gives me sort of what's known as an orthogonal representation, which is enough. Okay, so I have now, if I take L of G, the line graph of G, I get this graph on 18 vertices. The independence number is 4 because that's the size of the maximum matching here. Okay, the fractional chromatic number of the complement is written here, and this is because it's vertex transitive, so it's actually just the number of vertices over the clique number. Clique number is also 4 because this graph that we took the line graph of has degree 4, so then the clique number of the line graph is 4. Okay, so I get 18 over 4, which is 4.5, right? And these vectors, they give me a projective packing of value 18 over 4, right? Because there's 18 of them. right? And I divide by the dimension. So I get that this alpha p is equal to chi f of g bar, and I have attainment. Okay. And so actually what you can do here is you can take just two copies of this graph, and you'll get that alpha q is equal to 9 in this case. Okay. But this is bigger than twice alpha q of one graph, because for the single graph, for instance, do I have it here? What lowest theta is equal to? Well, anyway, alpha p is 4.5 for a single graph. So alpha q is at most 4, right? So somehow taking two copies doesn't just multiply alpha q by 2, right? So this is sort of a bit peculiar, right? You would expect that you just double it. So this is a sort of very interesting. The other interesting thing that happens here is that if I look at the quantum chromatic number, and we haven't gotten to this, we'll see this tomorrow. Since this has an orthogonal representation in dimension 4, it can be quantum chromatic colored with 4 colors. And then this, but the quantum independence number, as I said, is also 4, right? So then this trivial bound and chromatic number, which is number of vertices over independence number, right? If you consider the quantum analog of this, I would take 18 over 4 for this graph. That gives me 4.5, but the quantum chromatic number is smaller than that. So this quantum chromatic number and quantum independence number, they don't obey this kind of trivial inequality that you get. But if you replace alpha q with alpha p in that inequality, then it does hold. All right, I had 2 minutes left, so I'll stop.
Thank you. I have a question about that bottom word there.
Okay.
So you're saying that if alpha of g less than fractional chromatic number of g bar, we can build the separation. We can multiply g by copies and get a separation in there.
Well, you don't need just this, right? We needed to start it with this thing, right? We needed these n vectors in dimension d, such that the fractional chromatic number of the complement of the orthogonality graph is equal to n over d. But then if you have that and this, then you can build this separation.
And then you're saying that it's good to look for the orthogonality graphs of the Cohen-Specker sets.
Yeah, I mean, I think a Cohen-Specker sets are certainly a good place to look. Yeah. I mean, I'm not claiming that all of them have this property.
I wanted to say that it would be nice if they did.
Yes. I mean, yeah, I don't know. I haven't really thought about that.
Because if we have alpha and alpha q are different, we know that the set of projections in the quantum Cochlear matrix form Cohen-Specker set.
So the set of projections in what?
In the quantum Cochlear matrix.
Quantum Cochlear matrix.
Well, the projections that you define for the game, for the.
Okay. Yeah. Okay.
They form Cohen-Specker set.
Yes.
So, and then you say from here we can get separation, and then use Cohen-Specker sets. Maybe the other way around also could work.
Yeah. Maybe that's a good idea.
Okay. And there's a clock, and then I'm gonna.
Yeah. Thank you.
And then I'm gonna ask if somebody else has any questions. Your hand, I'll bring the microphone to you. No. Okay. If there are no more questions, let's thank David again.